We're going to start talking about stability of causal systems and using the Laplace transform and the Z transform. Oh, by the way, hopefully you got the message through Piazza that I have office hours during the reading period. Did everyone get that message? Yeah. Okay. Good. We only have 2 lectures left today and Monday. All right. Monday we're going to bring in the inverted pendulum demo into class. All right. I know you're missing class. Too bad. Okay. Let's look at an example here of a continuous time system. I'm going to give a block diagram to describe a continuous time system. So we have x of t coming in as the input to our system. And let's let this box here represent an integral. So this just integrates whatever comes in. Let's call this, here's the output y of t. And suppose you have some feedback from the output of this integral over here. And it gets added into x of t. And I'm also going to, suppose we have an amplifier right here. I'll just put, from now on, I'll just put a number on the line representing that gets multiplied, gets amplified. Previously, I put a little triangle thing for it. But I'll just put a number there. So this 5 means multiply the output of that sum by 5. Okay, so this is really just an example of some continuous time system represented as a block diagram. Previously, for a continuous time system, I used a circuit. If you go back a few lectures, I've used resistors, capacitors, inductors. This is a more concrete example, but this is still something that could be implemented. For example, this integrator can be implemented simply by using some sort of amplifier and a capacitor together. You can build a box that basically integrates an input. Okay, so this is easy to do. Now let's try to analyze what is going to happen with this system. First of all, just intuitively, you might have some idea of what's going to happen. Suppose you put some input in for a while. It gets accumulated in this integral. Okay, and then let's say you stop the input. X of t becomes 0. What's going to happen from then on? Does y of t all of a sudden become 0? Should stay the same. And we have this feedback, so actually it's what? Yeah, it continues growing, right? Exactly, because let's say the value was like 3 when you stopped the input, right? Well, it's going to hold on to that 3, but then the 3 will feed back here. It'll multiply by that 5. You'll have 15 at the input of your integral. So it's going to keep growing. Of course, as it's growing, it's going to then grow faster and faster. All right. So let's just write out an expression. What could we write out here? Well, we could follow around. We could say, since that's y of t, then this here is y of t. That's the same line, right? So at this point, we have x of t plus y of t. And at this point here, we have 5 times all of that, right? X of t plus y of t. And so right here, we have the integral of x of 5. Let's bring the 5 out. 5 integral of x of tau plus y of tau d tau. Okay. Now we're at the same line as y of t, so we get an equation here. So the equation is simply, actually, I'll stay with blue. The equation is that y of t equals that integral. Tau. Okay, so now, this equation tells us the dynamics of the system. And it's nice maybe to take derivatives here and have everything in terms of derivatives. So we get a y prime of t equals a 5 times x of t plus y of t. Okay, and this we call a differential equation. Sometimes maybe a standard form to write it in is to put y of t alone on one side and say y of t equals negative x of t plus a 5th of y prime of t. Okay, so it's a differential equation. It's an equation that has derivatives of y, more than one different derivative. That has y by itself with a derivative in this equation. Now, you may easily be able, this happens to be a simple one, so it may not be too hard to figure out what this is doing. It's usually, you might expect some sort of exponential growth. But let me point out something important here. This is an LTI system. Everything in here is linear and time invariant. And since it's an LTI system, then it's completely characterized by the impulse response. In other words, all we really need to know about this system is its impulse response, h of t, because we know that this is just doing a convolution of h of t with whatever input we gave. Okay, so that fully describes the system. And equivalently, since the impulse response fully describes the system, then equivalently the transfer function, which is the Laplace transform of this impulse response, h of s, fully captures the behavior of the system. Okay, we could have said the Fourier transform, but Fourier transform, why am I not wanting to jump to the Fourier transform instead of Laplace transform here? This happens to not be stable. We already said it's, the impulse response we expect is going to be something that grows. It does not have a Fourier transform. So really, Laplace transform is going to be just as easy to use as Fourier transform for this analysis, but it's also going to work if the system is not stable. That's the reason we're going to use it. Okay. So I want to generalize this problem and say, suppose you have an arbitrary constant coefficient linear differential equation. Okay, so you get something for free out of this class. Even though this isn't a differential equations class, you are actually going to learn, now that we have all these tools, solving this category of differential equations will be so trivial. It takes only 10 minutes of a lecture, okay? And yet these are maybe the most frequent differential equations you'll encounter. So in some sense, they're some of the most important ones. So that's nice. We have all the tools to do these differential equations. Now I put difference in parentheses because in discrete time, the equivalent, in discrete time you don't have differential equations, you don't have derivatives. But you have difference equations, and we'll analyze those. Okay. So let's look at, so first of all, of course I should note that if you have a constant coefficient linear differential equation, I guess maybe I should write what it is first before I start telling you about it. Here's an example. So let's look at the continuous time ones, the differential equations. Differential equation. Okay, they're going to be of this form. You have a sum of certain number of terms. This is not an infinite sum. K equals 0 to some constant m of constants and derivatives of x equals another sum of derivatives of y. Okay, now I don't want this notation to throw anyone off. I mean, it's pretty straightforward. What we're just saying is you have a bunch of derivatives of x equals a bunch of derivatives of y, and they each have, there's numbers tied to these. They're not time varying, so these b's are just constants. That's why these are constant coefficient linear differential equations. Okay, so of course, this up above was an example. You could just lump all the x's on one side, all the y's on another side, and you have it in that form. Okay, so any differential equation of this form we'll be able to solve in a flick of our fingers. Okay, so notice something. And by the way, we say that the order is m, if there are m terms here. So this is like an mth order differential equation. Okay, these are going to be LTI. All right, because the coefficients are constant and because of this linearity. These are LTI systems. All right. So what do we do with these? Well, let's take a Laplace transform of both sides. Okay, we know what happens, what derivatives are in the Laplace transform. That just is a multiplication with s. So that means that this sum, k equals 0 to m, bk, this just becomes s to the k of x of s equals sum ak sk y of k, y of s. Okay. Oh, but we can factor out the x of s and the y of s out of the sum. Okay. So pull the x out and the y out. And what if we cared about this? Y of s over x of s. Let me summarize this the following way. Y over x, well, that's just some simple algebra because the x and the y come out of these sums. And that just equals the sum k equals 0 to m of, we're going to get the a's in, the b's in the top, the a's in the bottom, bk s to the k over the sum of the a's. Okay, so these are polynomials. So first of all, why do I care about y of s over x of s? So you're saying they're always relative. Let me give you a more concrete reason I care. Because what do we know about the convolution rule? We know that the input x gets convolved with this impulse response h, right, to produce the output y. We don't know what h is, but we're trying to kind of get at what h is. Convolution rule says that if you take the Laplace transforms, that's just multiplication. X of s times h of s equals y of s. Well, if x of s times h of s equals y of s, then h of s equals this ratio. So this is an important thing to remember, that if you ever want the transfer function, remember this is the transfer function. It's the Laplace transform of the impulse response of our system. Okay? That is just the output in the Laplace domain divided by the input in the Laplace domain. Okay? So all of a sudden, with no effort practically, once you have the differential equation written out in this form, you immediately get the Laplace transform. Notice also that this is a rational function. I've been saying over and over that we only are going to care about looking at Laplace transforms for rational functions. Well, here we see that if we're analyzing a differential equation, it'll indeed be a rational function. Okay, great. Let's now, we'll take that further in a moment, but already we can get an expression for the Laplace transform. Let's just do the same thing for a difference equation. Okay, so a difference equation is going to be of the form, here what we're going to think of a discrete time system. I'll give an example later to make this more concrete. Again, how do we end up with a difference equation out of some system? All right, you can think back to when we talked about how to implement a filter using delays and feedback. That would be a good example where you might want to, that would be that filter design might be a system you want to analyze. You want to know if you've designed something stable, for example. And what you end up with in those cases is something of this form. Sum of bk, and it's going to be times x with delays. So x of n minus k. And that's going to equal some sum of the y's with delays. Okay, so again, if it's not clear to you, why would you ever end up with this kind of equation? We'll have an example soon. Actually, I can give you a little example. I mean, normally you would see it maybe written out in something like this. Yn you've analyzed some system and you found out that yn equals something like x of n, 3x of n plus 2x of n minus 1 plus maybe some y term, half of y of n minus 1. Okay, you might end up with something like that, and you can see that this is going to do something interesting. Like, let's say xn is an impulse response, is a delta function. So you want to calculate the impulse response. You can just follow this through one time step at a time. You have this feedback from the last output, and you could calculate what the y's will be at each time step. All right, we'll do that later. But you could also just rearrange these, put all the y's on one side, put all the x's on one side, and you get this more general equation down below. Once you have that equation, then, of course, take the z transform. And what you're going to get is, now, what is the time delay property for the z transform? By z to the power of the negative times the delay. So it's going to be z to the negative k here, x of z. And that's going to be z to the negative k, y of z. Again, you factor the x and y out, and you end up with h of z equals y of z over x of z equals the sum of the b's negative k, and over the sum of the a's. So you get a polynomial in the numerator and a polynomial in the denominator. Now, these are polynomials of z inverse. This is rational, but to find the poles and zeros, you should multiply out with z's so that you have positive exponents. Okay, so either one of these are going to be solved easily, and they all end up with rational Laplace or z transforms. Remember, I said that we define the z transform in a different way with a z rather than e to the s. And fortunately, the definition of the z transform is nice enough that it gives us rational z transforms for these types of systems. Okay, let's look back at our differential equation that we had in our example. Same example. Now often, so here's the example again, plus we had a 5 here, we had an integral here, we had the output feedback like that. That was our example. Now, we wrote out a differential equation and then we took the Laplace transform. In fact, it's often easiest to just take the Laplace transform in the first place. So for example, say what comes in here is x of t. Let's call that x of s. What comes out here is y of s. Okay, this is y of s. I mean, it's the same steps, but it just some people find this less confusing than writing out the differential equation. We would say this here, the integrator in the Laplace domain is simply a 1 over s. That's what it does. It does 1 over s. It's a multiplication by 1 over s. So then this becomes, 5x of s plus y of s. And this just becomes, whoops, that's not that. That's here. And this just becomes 5 over s, x of s plus y of s. And then you get the equality with y of s. And then you just solve for the ratio of ys over xs. Okay, same steps. But you could have just done this in the first place. Just go do everything in the Laplace. All right, and then you don't have to write out integrals and stuff like that. You just end up with 1 over s. Okay, now let's and of course then you say y of s equals, I'm just repeating the same type of steps, 5 over s, x of s plus y of s, and then that tells you that s minus 5 y of s equals 5x of s. And so you get that h of s equals y of s over x of s equals 5 over s minus 5. Okay. By the way, I mean, the work we had done above gets us there as well, right? We just get to this line here. We'd plug this into the formula we have for any differential equation down here. And we would get this exact same transfer function. So it's not like this was a really fundamentally different way. I'm just showing you could have just done it using the Laplace notation in the first place. Okay, so what does that tell us? Well, now I have up in the title of this lecture that we're talking about stability of causal systems. Okay, we're going to focus on causal systems because we're talking about, think of things in real time. You don't have non-causal behavior. That block diagram implies some sort of causal. It implies that if you don't put in, what I have implied by causal is that until you put something into this system, we'll assume the output was 0. Okay? Yes? Good. Let's do that next. Let's figure out what the region of convergence is. And that's where this notion of it being causal is going to be important. So if we assume implicitly that every system, and that's what we'll assume for this lecture and next lecture, that every system we care to analyze is causal, then there's only one region of convergence that could be causal. Okay? So let's look at the poles and zeros. Here, I'll make a note of that. Assume causal. Okay, so what are the poles and zeros here? Well, we have the formula. So are there poles, are there zeros, and where are they? There are no zeros. Good. So this is a real part of S. Yes, and there's a pole at S equals 5. Perfect. Imaginary part of S. We've got no zeros. One pole. All right, and that pole is right here at, we'll use an X to mark a pole, and that's at S equals 5. So I guess I'll just mark 1 so we get a sort of a scale there. Okay, so there are two possible regions of convergence when you have one pole, because the pole bound is the boundary of the region of convergence. You could either be to the left of the pole or to the right of the pole, but if the system is causal, then it has a right-sided impulse response, and that means its region of convergence can't have a right boundary, so it's always to the right of the poles. All right? So this is the region of convergence for that system, because we've assumed causal. So now, what can we say about it being stable? It's not stable, right? It's not stable because the imaginary axis is not in the region of convergence. In fact, there is a simpler summary statement that we can make about whether or not it's going to be stable in these cases. Stable if and only if, and here I mean under the assumptions we have here. Suppose it's a differential equation, meaning it's a rational impulse response. I mean a rational transfer function, and it's causal. Okay, so of course we're assuming causal and rational. And of course, any differential equation is going to be rational here. So causal and rational, then stable if and only if. What about the poles? I think we said this in a previous lecture, actually. Yes, all poles in left half plane, which means real part's negative. So that means real part. So all you have to do once you see the poles is you can easily tell if it's stable. Are the real parts all negative? Okay. What if it was, this is for continuous time. What if it was discrete time? Let's come up with the rule there about the poles. So the Z transform, all poles in, okay, so this is continuous time, and this is discrete time, meaning the Z transform. What would the rule be in the Z transform? Yes, all poles in the unit circle. Okay, so that's really what we want to check for if we want to know if this is stable. Of course, we already knew that that system above was not stable. We can take this further, and we can actually calculate the impulse response in time. I will give us what? Okay. Oh, to something you'd seen before about poles.
Yeah. Well, it's like whenever you're doing like time series stuff in a quantum metric, you can only deal with basically like long-term stable systems, and the key for that is that you have like a unit root test that like the roots of your polynomial have to be within
the unit circle. Yes, it's the same mathematics. Yep. Yeah. Okay. So we can see here that if we want the time domain, we can invert this, and you can just take my word for it that in time, this says what? H of t equals 5e to the 5t u of t. You can do the Laplace transform explicitly on this h of t and see that you'll get 5 over s minus 5. Momentarily, I'll show you how we systematically can go invert this. Okay, but so this is actually the impulse response for this system here, which is the same one with the one we started with. So now we know exactly how it responds to an impulse. And we know that any input gets convolved with this. Okay, great. So there's a lot we can do, and all it took was using the Laplace transform to very quickly get a transfer function. All right. Let's now do an example in discrete time. Okay. All right, here, again, I'm going to use a block diagram to try to make it seem a little bit real here, not just start with an equation. So let's say you have, again, I'm going to use these blocks with D to mean a delay of 1. Yeah. Only offline things. I mean, real-time systems will be causal. But if you're doing something like processing some saved data, of course you can do like non-causal stuff. Yeah. But in control, you pretty much always have to assume causal. Okay, so let's do it like this. Put a couple numbers here, meaning you multiply in those spots. Here's y of n. And now I'm going to put some, so far I've drawn something that looks like what we had drawn for an FIR filter. The impulse response here would be finite. So you could use this to implement an FIR filter, but remember that if we had feedback like this, take the y, put it through some delays, and go like this, then we no longer have a finite impulse response in general. I'll put some more numbers on here to make it interesting. Okay, but we now have an impulse response that is usually infinite. In fact, this feedback could cause the system to be unstable. Okay, now I could do the same exercise. I could follow through each thing here. I could say, well, I know what this signal is. This is x of n minus 1, okay, because of the delay. And this down here will be, and that means this is y of n minus 1. This is y of n minus 2. This here is going to be x of n plus 3 y of n minus 2. All right. This sum here now is going to be a little more complicated. Let's say, let's take it before the 1/4. It's going to be 2x of n minus 1 plus what came in to the left, x of n, plus 3y n minus 2, plus what's coming in from the bottom, 11y of n minus 1. Okay, then multiply by 1/4, and that should equal yn. So you get your equation. All right. So now we have, and you can see it's a difference equation, right? It's a constant coefficient linear difference equation. Great, so the next step is to actually, so So let's write out the equation we get. Y of n equals 1/4 times this whole thing. 2, just repeat that there, plus xn plus 3y n minus 2 plus 11y n minus 1. Now there's a few things we might want to do here. Of course, I really want to just jump straight to the z transform. Oh, did I miss something? Xn minus 1 right there. You're saying where did it go? What is this it?
Oh, yeah.
Okay. So I want to jump straight to the z transform because that's where we'll learn the most out of this. But let's pretend we don't know that for a minute. You might want to just manually go through and calculate like the impulse response one step at a time. We could try to do that. Let's do a little aside here and say impulse response. How would we get at the impulse response of this thing? Well, we assume nothing happened until time 0 because it's causal. At time 0, there was a 1 came in here. So we can either follow the block diagram and see where the 1 propagates through. You know, time 0, there's a 1. That means this is 1. That means you get a 4th out at time 0. Okay? Or we can just use our equation. We already derived an equation. So let's say, what do we have at time 0? Well, these were all 0. That was a 1. That was a 0. That was a 0. We get y of 0 equals 1/4. Okay? Then we get y of 1. And we go through again and we say, well, now let me give myself some space. I'm going to mark these again. So at time 1, for n equals 1, so that was n equals 0, right? N equals 1, this is going to be a 1 there, and that's a 0. Are you following, right? Because it was a delta function. Xn was a delta function. And this is still 0, but that one comes from before. That was a 4th, so it's 11/4, right? Is that not right? Oh, yes, that should be a 2. Yeah, I see what you're saying. I was just writing the symbols. All right, fine. I'll just say 1, and I'll say a 4th. 1, 1/4. Then you multiply all by their coefficients, and you get that y of 1 equals, you get a 2 times that, times a 4th, so you get a half from this one, and you get 11/4 times a 4th, so 11/16. Okay, so whatever, half plus 11/16. Okay, and we could do this, but you might see that you don't expect this to actually end. It's going to be infinite, because as we keep going, the y's will never clear out. The x's stop. On the next one, the x's are all 0s, but the y's will never clear out. You'll keep getting feedback. Okay, but we could go through and actually calculate step by step what the impulse response is. We just never finish. The z transform will give us a way to give us a formula for it. Okay, but you know, depending on your setting, maybe all you cared about was knowing what the first few samples of your impulse response are. Well, you can do that very directly. All right, so that's a little aside. So to know that it doesn't actually end in a finite amount of time? Yes, the convergence to 0 is going to be equivalent to it being stable. So we'll just use the z transform to decide that. Yeah. So let's now jump to what we wanted, which is the z transform of this. So now let's use z transform. And we take our above difference equation, and we just plug it into the z transform, the formula we have, and we get that h of z, which is y of z over x of z, is going to be, and of course we would need to just collect. Let me collect the terms together. So if I rewrite this in another way, I'm going to have 4y of n minus 11. Y n minus 1 minus 3y n minus 2 equals xn plus 2x n minus 1. I just collected all the x's and y's over, right? And then I can very easily get my z transform formula. 1 plus 2z inverse, that's coming from this right side, over 4 minus 11 z inverse minus 3 z to the negative 2. There's the z transform. Now what we want are the poles and zeros, so the next step here would be to first of all, let's make the z's positive exponents, all right, just so everything's clear. So this becomes a z squared plus a 2z. I multiply the top and bottom by z squared. 4z squared minus 11z minus 3. Okay? Now I want to factor. Well, the top is easy. The bottom takes some, a little bit of effort. But you'll see that the factorization is this. We get a z times z plus 2. That's easy. And then in the denominator, let's take the 4 out. So we get z minus 3 and a z plus a 4th. So now we can easily see what the poles and zeros are. All right? And we have this constant 1/4, which doesn't affect stability. Okay, so again, as before, we assume causal. So that's going to tell us which region of convergence we care about. And so here's the plot of the poles and zeros. So this tells us everything about our transfer function. Real part of z here, imaginary part of z here. Okay, and we have 2 zeros, right? It didn't look like 2 zeros maybe in this first expression with z inverses. But it actually has a 0 at the value z equals 0. So you've got a 0 there, and you've got a 0 at z equals negative 2. Okay, I should label some things here. This is negative 2. Let's put 1 because a unit circle is always important to us. All right, that's maybe not to scale, but okay. And we have now 2 poles. We have a pole at z equals 3. So that's way up here. And we have a pole at z equals negative 1/4 right there. Okay, so the poles mark the possible regions of convergence. So if we didn't know it was causal, we would have 2 possible boundaries of the region of convergence, right? We could either be the very inward one, which would be the left-sided impulse response. We could be the one in between, which is a 2-sided impulse response, or we could be the outside one. But because it's causal, it's going to be the outside one. So we have this is the region of convergence. And now we can say, is it stable or is it not stable? Let's see, someone who doesn't answer usually. We only have Haley. Do you think that this is going to be stable? No. Why is it not stable? So yeah, well, actually, the outside boundary is not what it needs to be stable. So it's okay, that part's okay. But to be stable, this unit circle would have to be in the region of convergence. Yeah. So because we have a pole outside the unit circle, that caused this to be unstable for causal systems. Okay, great. So now let's talk about a couple more things. I want to talk about how you do an inverse to get the time domain representation. Now, often you actually don't care. You don't care exactly what the time domain impulse response is. You care about what happens, whether it's stable and what these poles and zeros look like. But we should know at least how you could get the impulse response in the time domain, how you do the inverse z transform or Laplace transform. So we'll do that. And we'll also, if there's time, talk about something that's probably even more important. Actually, maybe I should just go right to that. Maybe we should do the inverse next time if we run out. Because what could be more important is saying, given these poles and zeros, can I tell, if it was stable, all right, could I at least understand what the frequency response is going to look like, meaning the Fourier transform? We know in principle that can be done, right? The Fourier transform lives on the unit circle. We just need to evaluate it on the unit circle. But I'd just like to reinforce that that can be done easily by looking at the poles and zeros. You can get an intuitive understanding of what's going to happen in the frequency response. So let's see, what next? Actually, I think I will go ahead and go the order that I had planned, which means we'll just do the inverse here. We might have to do the Fourier transform frequency response next time. Although in general, that's maybe more important, like the more important thing to be able to do. Okay. So first, before I give the method of doing the inverse Z transform or Laplace transform, I want to show you something fun. This is and useful. We're going to just use long division to actually learn something about. So we have the Z transform here, right? Through long division, we actually can get some of the values of the impulse response very quickly. All right, and that will be it'll be equivalent to this method we did up here. We said we could run through the system one step at a time and get values of the impulse response one step at a time. You can do that equivalently from the Z transform, and let me show how. Suppose you take, okay, we have this. We have that h of z, I'm just going to repeat what we have above here. It equals 1, or actually, sorry, it equals z squared plus 2z over, what was that? 4z squared minus 11z. 11z minus 3. Okay, we have this. Well, what if we write this out as if we want to go and do long division on this thing? So we have the numerator in here, and we want to divide by 4z squared minus 11z minus 3. And we do this one at a time. So we take the largest z squared term, and we say, what should I multiply by this polynomial? If I'm just, long division means care about the first term first, right? So in other words, if I multiply this whole thing by 1/4, okay, then that's the result of multiplying this denominator by 1/4 is going to be, now let's write it out here, sorry. It's going to be z squared minus 11/4 z minus 3/4, right? That's the product. And what do? I subtract it and get the remainder. All right. So those first parts cancel as I designed it to do. And we get 19/4 z plus 3/4. That's the new numerator. So then I do the same step. I say, what do I multiply here? Well, I multiply 19, so I do plus 19/16 z inverse. So if I multiply this polynomial by that number, then I'll cancel this largest term. That's the idea of long division, right? So I'm going to get my 19/4 z here, but I'm going to get other terms as well. In particular, I'm going to get minus 11 times 19 over 16 minus, and then I get another term here, 3 times 19 over 16 z negative 1. And of course, the idea here was these canceled on that step, these cancel on that step, and I would keep going. And the reason I would have to keep going, I'd never end, is because it's actually an infinite impulse response. So I could rewrite this, like what have I done here? I've said that h of z, I can put it all up above here, right? Take all this, put it here, and say this equals 1/4 plus 19/16 z inverse plus the part I haven't finished, right? That should, you always subtract this line. So that means that this is going to be plus, it's going to be like 11 times 19/16 minus, plus 3 times 19/16 z inverse over the same denominator we started with, 4z squared minus. All right, so I've done a little bit of work. I've done some of the long division. There was no need to stop there. I could do as much as I want. The point is this. These terms here, we know the inverse z transform of these terms. That just becomes 1/4 delta n, and this becomes plus 19/16 delta n minus 1 plus And then this part doesn't start until after time 1. Okay, so what I've done by this long division is I found out this is the value of the impulse response at time 0. This is the value at time 1. And I could have found as many as I wanted. I could just continue the long division. All right, so this actually is the same, as what we were doing up here. And in fact, we should get the same answer. If you add those together, you get 19/16. Okay, so not necessarily any easier, but this is a way to get out values of the impulse response one at a time directly from the Z transform. What do we actually want to do to, by formula, get out the entire impulse response? So that here, this will be the inverse Laplace transform or Z transform. Now, but this is going to be, we're going to learn specifically how we do this for rational functions. It'll be easier than doing any integral. We won't need any integrals here. All we need is a handful of very useful Laplace transform pairs that we remember. Very small handful. So here are important transform pairs. All right. The pairs are like this. E to the negative at u of t. Under the Laplace transform, I won't even draw arrows. Laplace here. Here's the Laplace transform of each of those. We have a little table. This is 1 over s plus a. And of course, if it's causal, then the region of convergence is that the real part of s should be right of the rightmost pole. So real part of negative a. I maybe didn't even need to write that. Right? Well, okay. Here's another one. The non-causal version of that we might as well have in our table. If for some reason you wanted a non-causal inverse to your Laplace transform, you would have to use this same formula, but the opposite region of convergence. Of course, since we're mostly going to be dealing with causal systems, that second one is not going to matter much. But here's something more important for us. If we have t to the k, e to the, so it's a polynomial times an exponential, the Laplace transform of this has k poles all at the same place. Actually, k plus 1. K plus 1 poles all at negative a. And it has a constant here, k factorial. Okay, and of course the real part of s is, and since we don't care about the non-causal version of this Laplace transform, I'm not even going to put it. Okay, so really that's all we need to know for Laplace transforms. Let's look at what we need for the Z transforms here. We also need some pairs over here. We need, well, there's some we already know. Delta function of n is just 1. Or more generally, delta function of n minus k is just z to the negative k. Okay. We have that a to the n, u of n, and a does not have to be real here, that this is always going to be 1 over 1 minus a z inverse. And of course, since this is right-sided, you already can figure out that the region of convergence will be everything outside of the pole, like this. Okay. I'll give you the complementary one, the one that's not causal. That's this one. And it's the same formula, but it's got the opposite region of convergence. Again, not something we'll really care for much if we're doing real-time control. And then lastly, what you need to know is if you have a polynomial in n. Actually, I won't even do the high order polynomial. If you have n times a to the n u of n, okay, that this one becomes, again, you get 2 poles at the same location. 1 minus a z inverse squared. And it's a z inverse up here. All right. So with this set of Z transform pairs, we're prepared to do the inverse of any rational Laplace or Z transform. The method is the following, and we'll practice it next time because we're out of time. The method is partial fraction expansion. So in other words, you would take your Laplace your Z transform, like we could take the one up above that I have right here. Okay, you would take let's write that out. You take whatever your Z transform is, like Z squared plus 2Z over. Actually, it's better if I factor the denominator. So what was the factored version? It was 4Z minus 3Z plus a quarter. Plus fourth. And what you do is you say this equals a sum of two fractions, an A over Z minus 3 plus a B over Z plus a fourth. Okay? Now I just need to figure out what A and B are, and I can use algebra to figure that out. Once I find out what A and B are here, and it may happen that actually next time you'll see I should have factored out a Z here. Z, let's get rid of this one. Z plus 2. All right. Then once you find out what these constants A and B are, then you can just use this table here to invert it, because you'll have things of the form a single pole. Okay, these are each a single pole. So you can just use this table to find out the inverse of each part. Okay, we'll do that next time. So really it's just an algebra exercise to go through and expand into a sum of fractions of single poles, and then each one you can just invert from the table. That's how it works.